All right, this is question 2 of the 2019 AS Physics Paper 1 from AQA. Again, my class did this as a mock, so this is so that they can see what they've, or how they should have done this, or how they could have approached these questions. Okay, so question 2 is relating to a battery, and we're given a bit about the battery. It has an EMF of 7.4 volts, and it has using to power a heating element, and the heating element has a resistance of 3.7 ohms. And in the first question, I need to calculate the energy dissipated in the heating element, and I'm told that I've got a current of 2 amps that's on for 240 minutes. So what I'm going to do is I'm going to use the equation for power dissipated by a resistor, which is I squared R. So that is 2 squared times 3.7, which I don't feel like mathing it in my head. 4 times 3.7, 14.8 watts. Energy is power times time, so 14.8 times 240 times 60 is 2.1 times 10 to the 5 joules. Just be wary of your significant figures. Don't want to lose a mark unnecessarily. So, moving on. The length of the heating element. So actually, I should say on this one here, it doesn't matter what formula you used. If you use power as I times V, if you used V squared over R, because it's the only resistor that's in the circuit, and there's no internal resistance, we could use any one of the formulas that we want. Just I squared R is the one that I'm used to using for this kind of question. So, here we go. Length of a heating element needed is about 0.85 meters. The designer considers carbon fiber tape for the heating element. Whether or not this is suitable. So, R is equal to rho L divided by A, where rho is resistivity, L is the length of the wire, and A is your cross-sectional area. So 2.0 times 10 to the minus 5 times 0.85 divided by 4.9 times 10 to the minus 6. Okay, 0.85 divided by 4.9 times 10 to the 6 minus 6, 9. You can see this program likes my handwriting about as much as you guys do. So equals 3.4, so 3.5 ohms. So we're in the right range. It's just whether or not they want you to say that it's okay or not. So if this is your answer, I would accept that you could say, yeah, it's close enough. I would also accept if somebody said no, because you'd want the resistance to be higher so that you don't have more current flowing. Um, as long as your conclusion is reasonable, you'll get a mark. If you calculated 37 ohms and said yes, you would get no marks for that. But here, I think that you could say, yeah, this one is fine because it's about 3.5 ohms. We want 3.7 ohms. It's close enough. Although you won't be, or you'll have a current slightly higher than 2 amps is what you'll end up having with this one. Okay, so we've got a light emitting diode, and we've got a characteristic graph for said LED. The circuit is designed so that the potential difference is 2.25 volts. Calculate R. So, here's what I'm going to go back to my diagram for this. So, we know that this battery is 7.4. Okay? We know that we've got 2.2 volts here. So, the voltage across R has to be 7.4 minus 2.2. And that is 5.2 volts. Okay, so, oh, look at, I've got a current that's got, or a graph that has current and voltage on it. Well, the potential difference in my LED is 2.2. Oh, and that's really convenient because it looks like it's right on that line. And that's 15 milliamps. So the trap there is milliamps. Okay, or even just not realizing, oh, hey, I should read the graph. So just be careful. So we know that resistance is V divided by I. So 5.2 divided by 15 times 10 to the minus 3.